All right, just looking at the schedule. So I'm supposed to be on Wednesday. I'm supposed to be doing chapter 12 and 13, so I'm behind here. So let me get caught up a little bit. I'm probably going to lecture a little on Thursday, tomorrow. Tomorrow we're going to do some experiments. We'll see how that works out. I'm most likely going to do this. I'll probably move these labs here. You know, I want to move these probably to Thursday here. And then we'll just bump everything out this way. So just have the labs on Thursday here. I'll probably leave these other labs down here on Monday. Okay, so move to Thursday. I went to the lab today to take a look. I think we can get these going. Sorry about the background noise there. All right. So are there any questions about that? I'm probably gonna have to post this in Piazza since a lot of people aren't here. Okay, were there any questions to get started? All right. No? All right, let's get going. We're going to do some more. When we look at the lab schedule, actually, let me go back. When we look at the lab schedule, we're going to be doing more chemical reactions. So for example, experiment 3, we're doing observation of reactions. Experiment 6, some common chemical reactions. Experiment 12 deals with lots of chemical reactions here, and experiment 13 deals with oxidation, reduction, redox reactions. So we're doing a lot of chemical reactions. So we'll get a lot more practice with chemical reactions as we go along. And so I'm going to leave chemical reactions for right now. 8 and 9. 8 and 9, you know, those are important chapters here. We finished chapter 10. We're looking at 11, 12, 13 for this week. But let's go on here. 19, I probably don't need that much time for. So we'll probably push these back a little bit. Let's take a look at some chapter 10 problems. And so going to chapter 10, let's look at what types of homework problems there are in chapter 10 here. All right, the first step of the Oswald process here for manufacturing nitric acid. Nitric acid is an important acid. Nitric acid is an oxidizing acid, as we talked about earlier. And it's very common. In fact, I remember one time I was driving on the freeway and the freeway was stopped because there was a chemical tanker on a truck. And there was a spill that was involved in an accident. And there are plumes of orange smoke coming off the truck. This is when I was studying. I was in like general chemistry at the time. And I remember seeing those plumes of orange smoke. And then I was stuck on the freeway, and then the news crew was there. And I was like one of the first cars. So I was watching the news crew guy talking about the spill. And he's saying, oh yeah, there's a spill of hydrochloric acid. I thought, that's impossible. That can't be hydrochloric acid, because hydrogen chloride fumes are colorless, you know, for one. And I was thinking, I've seen nitric acid before, because if you have a bottle of it, then you can see kind of orange, you know, orange from nitrogen dioxide, just from coming off the top of it sometimes, especially concentrated nitric acid. So I was thinking, that looks like nitric acid. But anyway, he kept saying it's hydrochloric acid, hydrochloric acid. but you know. And the NO2 smells like, you know, it smells like sulfur in a way, you know, it has a very corrosive, like sulfur dioxide and sulfuric acid, that kind of corrosive taste, smell to it. And so this is why, you know, at the Grand Camp explosion in Texas City, a lot of people were saying there was a very sulfur-like smell in the air, but it wasn't a sulfur smell, it was a NOx smell, you know, oxides of nitrogen. A really smoggy smell. All right, so this is the first step, so it's multi-step. So they take ammonia and oxidize it with oxygen. So in other words, it's burning ammonia. When you burn ammonia, you're going to form oxides of nitrogen. And there are lots of different oxides of nitrogen. This one's nitric oxide, you know, NO. NO is very common pollutant. Also, you know, common in regulation of your circulatory system, blood, you know. H2O, and so this is like combustion of hydrocarbons. You know, when we combust hydrocarbons, you know, this is a nitrogen hydrogen containing compound. But when we combust hydrocarbons, when we combust hydrocarbons, we're looking at, like, for example, methane. If we combust like something like methane, you know, with two O2s, this is going to produce CO2. CO2 is an oxide of carbon and water, like that. And so this is very similar. Do you see the similarity in the two reactions? This is combustion of this ammonia. This is combustion of methane here. We produce oxides of nitrogen, we produce oxides of carbon. It doesn't need to be CO2, it could be carbon monoxide, you know. That's pretty much the only one. Nitrogen is very rich, you know, there are so many different oxides of nitrogen. It's got extremely rich, what we call redox chemistry. The NO is colorless. This is a CCG. CCG stands for clear colorless gas. And it's rapidly oxidized by O2. So we'll take a half mole of O2 for every mole of NO, you know, something like that, and we'll form NO2, you know, or just O2. This is not balanced because I got 4 NOs there. And so I'm really, I just guess, I need, let me properly balance this. Let's get rid of the 1/2. In order to properly balance it, I'll need 4 more oxygens. So I'll need 2 O2s. Let's make 4 NO2s here. 2 O2s. This NO2 is that orange gas, you know, and it's poisonous, of course. And it's also got that sulfury smell that they were talking about in the Grand Camp, Texas City disaster explosion. All right, the states here, you know, ammonia is a gas, methane is a gas, O2 is a gas, you know, NO is a gas. CO2 is a gas, but H2O under normal conditions is a liquid. Of course, it could be a gas, you know, it depends on how much heat, but eventually that gas is not going to stay a gas under normal conditions because it can cool down and make a liquid. So use this equation to answer all parts of this question. So how many moles of ammonia will react with 95.3 moles of oxygen? And so we just need the mole ratio. So this is a mole to mole conversion, you know. 95.3 moles of O2. What's the mole ratio? The mole ratio is 4 moles of ammonia for every 5 moles of O2. Yeah. And so we just times this by 4/5. What does that equal? And so 76.2. Okay, moles. Let's move on. How many moles of nitrogen monoxide will result from the reaction of 2.89 moles? So what's the mole ratio? It's a 4:4. 4:4 is a 1:1, so the same. 289, 4:4. I write it 4:4. You know, I don't simplify this to 1:1 because, you know, you want to keep variation to a minimum. That way, if you keep variation to a minimum, it's a lot easier to catch mistakes. You know, so I leave it as 4:4. I don't change it. If 3.35 moles of water is produced how many moles of nitrogen monoxide will also be produced? So 3.35 moles. So it's going to be a 4 to 6 ratio, 4 moles of NO for every 6 moles of H2O. 4 to 6 ratio. 4 moles of NO, 6 moles of H2O. So this is a mole to mole, moles of A to moles of B type conversion. Magnesium hydroxide is formed from the reaction of magnesium oxide and water. Okay, this reaction is a Lewis acid-base reaction. We haven't talked about this particular reaction here, but it's a reaction between magnesium oxide, which is solid, and water. Oxides aren't soluble in water, but there's potential for reaction here. And there are two ways of thinking about this. The two ways of thinking about this reaction is actually 3 ways. There are 3 ways of thinking about this reaction. One way, the best way is this is a Lewis acid-base reaction, and that gives you the best visual picture of what's happening. And it's much easier to understand theoretically with a minimum of memorization. That would be it. The other ways of thinking about this is a, magnesium oxide is a weak base, right? But oxide itself is a powerful base. This is a powerful base. And the reason that this is a weak base is because of its insolubility. The oxide's locked up into a lattice, so the oxide's not free to react and attack things. If the oxide were free to react and attack things, this would be a very powerful base. That's why soluble oxides are very strong bases. But because the oxide's locked in the lattice, it's unreactive. However, it's still, if water comes along and knocks, collides, so let's say a water molecule comes along and collides with an oxide that's locked in the lattice, then there's going to be a reaction, here. And so there's some lattice structure here in the crystal. There's a crystal of this stuff. And so it is possible. It's just not going to be nearly as reactive as if it were free in the aqueous state. Free means it has translational motion, but in this particular case it doesn't. And so one thing is, if oxide's a powerful base, it's going to pluck the hydrogen off. And so it'll pluck a hydrogen off there. So we'll have a hydroxide here. Now what's left with the water? What's left of the water is another hydroxide, because it's lost that. And this MgOH, this whole unit is going to be positively charged because magnesium is 2+, hydroxide is 1-. So this whole thing will be positively charged. And so what's going to happen is this hydroxide is going to attach to that and do that. And so this is a Bronsted. Magnesium hydroxide is insoluble. So this is Bronsted way of thinking about it. Lewis will talk about, in fact, I have calcium oxide, I think, is my Lewis example, calcium oxide and water. We'll go back to that later. And so there are 3 ways of thinking about this reaction. One, Lewis is probably the best, although, this is okay too. Oxide wants to pluck off that hydrogen off water. It can't really easily because it's locked in the lattice. Can't go over and attack it. Water has to come to it. All right. Then that's Bronsted. And the other way of thinking about this as a metathesis. Now, metathesis involves ions, and water is not an ionic compound. Water is what we call a molecular compound. But one thing I did when I was a Chem 1A student was, I was taught this. Think of water as a hydrogen ion with a hydroxide ion. And so this fits the AB plus CD type format. If we go with that, AB plus CD, then we'll have magnesium with hydroxide. Well, magnesium is a 2+, hydroxide is a 1-. So we'll need 2 hydroxides for that. And this is insoluble. Calcium, barium, and strontium hydroxides are soluble, but magnesium hydroxide is not soluble. And then we have H with O. Well, H with O is just going to form, H2O. And so this is what we're going to form here. And then to balance it out, how many hydroxides do I need? I'm going to need 2 hydroxides, so I'm going to need 2 waters here. Well, if I have 2 waters there and 1 water there, then one of these waters will cancel out. And that will give it to me. Okay, that's one way. And so if one of those waters cancels out, then the net reaction is MgO solid plus H2O liquid goes to MgOH2 solid. That's one of those. So we can think of it as a metathesis as well. So 3 ways of trying to visualize this reaction. How many moles of magnesium oxide are needed to form 0.884 moles of magnesium hydroxide? So magnesium oxide and magnesium hydroxide are 1 to 1. So it's the same. Let's take a look. It's a 1 to 1 mole ratio. So it's the same. We have to get the balanced chemical equation. When sulfur dioxide reacts with oxygen, sulfur trioxide forms. How many moles of sulfur trioxide are needed to produce 3.39 moles of sulfur trioxide if the reaction is carried out in excess oxygen? Well, sulfur, oxides of sulfur, we have different ones. I guess and this is, which oxide of sulfur do we make? Because sulfur, remember the oxidation state of sulfur varies from -2 to +6. And so, in this case, sulfur trioxide, what is that? So sulfur dioxide, SO2, reacts with excess oxygen. So excess, we use XS, the letters. That means we have extra, plenty of oxygen. And so we should get complete combustion. Now, SO2 can burn. Carbon monoxide burns too. We can burn carbon monoxide gas in excess oxygen to form carbon dioxide gas. This is one way of getting rid of carbon monoxide. Carbon monoxide is much more poisonous than carbon dioxide. Carbon dioxide can get poisonous at high levels. High levels of CO2 are very bad for you because CO2 is an acid. It causes your blood pH to drop. That kind of stuff causes problems. Carbon monoxide can burn, but carbon monoxide attaches to your hemoglobin and doesn't allow oxygenation of your blood. That causes you to basically, what do they say? Die by asphyxiation, essentially. So in this case, it's going to form sulfur trioxide here. Sulfur trioxide. Now, what's the oxidation state? Well, when we look at the oxidation state here, we can see it's not completely oxidized because sulfur is going to be +4 here. And over here, it's going to be +6. So this is the max. We aren't going to go beyond this, But you might say, hey, I've gone beyond this, with sulfate. Just hold on one second. I'll be right there. All right, sorry about that. Let me answer a question. So you might have said, hey, I've seen sulfur with 4 oxygens, but yes, you have seen sulfur with 4 oxygens, but the big difference here is it has a 2- charge. We have sulfur with 4 oxygens, but it has 2- charge. So what's the oxidation state of sulfur? There, the oxidation of sulfur is, +6. Now, net charges, I don't put in parentheses. Whenever I do oxidation states, I always put those in parentheses. Oxidation state, that way you have a consistent system. People in general put oxidation states in parentheses. Not always, but in general, it's just a rule. There are exceptions to the rule, but it's good to stick to the rules. That way you don't, you do things consistently, so it's less chance of making a mistake. So both of these are maxed out. And sulfur trioxide is maxed out. That's complete combustion with excess oxygen. All right, this is a 1-to-1 ratio, 1-to-1 mole ratio. So, actually, why are they doing 2 to 2? They're doing 2 to 2 because of this. They said excess oxygen, but this is stoichiometric oxygen. When we do it with stoichiometric oxygen, then it's O2, 1O2, you know? When we do it with excess, there's more than, like there might be two O2s and not all of them react, so you have some left over. You know, that's a limiting reagent problem we were talking about in this chapter. But this is balance. This is the stoichiometric amounts. The stoichiometric amounts are just the right amount. You know, when you're doing reactions, you'd like to do the stoichiometric amounts. That way there's no waste. You know, if you're using excess oxygen, then some of it's wasted. And so this is stoichiometric. They shouldn't have just said, they should have just said it was oxidized, you know, completely or something. The first step in the Oswald process, okay, we saw the Oswald process before. Okay, now what we're doing is we're doing a gram, you know, so 268 grams of oxygen. How many moles? This is kind of ridiculous. This is a gram to mole to mole. You know, this is going in baby steps, you know. And so grams of oxygen to moles of oxygen, 32 grams, you know, to 4 sig figs. We got to make sure we get the 4 sig figs right. I don't want to see this. For example, you know, a lot of people get lazy and they just say, okay, 1 mole of O2 is 32 grams of O2. This is a totally different number than this. These two numbers aren't the same at all. And this is only the 2 sig figs. This is the 4 sig figs. And so I don't like to see that. Here, these are exact, you know, the perfect amounts are 4 to 5 mole ratio here. And so this is a gram to mole to mole conversion. So baby steps. If the reaction consumes 31.7 moles of ammonia, how many grams of water will be produced? So we go moles of ammonia to moles of water using mole ratio. Moles of ammonia to moles of water, you know, 4 moles of ammonia, 6 moles of water. And then moles of water to grams. So moles of A to moles of B, moles of B to grams of B. And the molar mass of water is 1802, you know, oxygen 16.00, and then we have 2 hydrogens at 101 each, so it's 202, 1802. How many grams of ammonia are required to produce 404 grams of nitrogen monoxide? Okay, so again, 404 grams, and so this is the way I do maps, stoichiometry maps. Sometimes it's like this. I go, okay, I have grams of NO, and then I go from grams of NO to moles of NO, and then moles of NO to what? What am I going to? Ammonia. And so from moles of NO, I go to moles of ammonia over here. And then from moles of ammonia, I could go wherever else. I could go to number of ammonia molecules. I could go to grams of ammonia. There are a number of places I can go on the map. But this is just stopping here. And so grams of NO to moles of NO. Nitrogen's 1401, oxygen's 1600, so it's 30.01. It's 4 to 4 mole ratio. And then ammonia, nitrogen's 1401, 3 hydrogens is 303. So it's 1703, 229 grams. So this is this is the standard stoichiometry. This is grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. And so this is your standard stoichiometry problem right there. This is what we call the theoretical amount. You know, if I wanted 404 grams of NO, then theoretically I need 229 grams of NH3. So if I want 404 grams of NO, I better start off with 223 grams or 229 grams of ammonia. That's assuming we have a 100% yield. You know, that's assuming everything works out perfectly. But in lab, oftentimes things don't work out perfectly. You know, let's say in lab, let's say at home, you want to bake 100 cookies for an event. But it's hard to not to eat them, when you're making them. And so you probably should bake more than 100 cookies. You probably should bake 103. Well, the same thing goes in chemistry. You want 404 grams, but you might lose some, you know? Depends on how much you might lose. So you might start off with more in case there's some loss, in case you don't have a perfect yield, in case you lose it. And you have to kind of guesstimate how much you might lose in that case. You could guesstimate it based on, let's say, each time you make cookies, you eat 3 of them. And then that's a good guess. Well, let's say each time you make NO, you lose about 5%. Then you have a pretty good guess. Well, you better start off with 5% more ammonia, But this is theoretical, what we call the theoretical. If your book's going to call this the ideal, this would be the ideal. If 6.41 grams of water results from the reaction, what will the yield of nitrogen monoxide be? Okay, so if we made 6.41 grams of water, if we made 6.41 grams, how many grams of NO must have formed? And so this is the same thing, with stoichiometry, we can relate any of these two things. And so we go from grams of H2O to moles of H2O. And then from moles of H2O to moles of NO. And then from moles of NO to grams of NO. That's the way. So we're just going backwards here, kind of, or figuring out, in parallel how much NO is made in conjunction with the water. So grams of water to moles of water to moles of NO to grams of NO. It tells us here in the grams. This is dynamite. Dynamite is nitroglycerin here. Nitroglycerin is quite unstable. Take a look. Do you see, what's this? What do you know about nitrates? Or nitrates? What do you know about nitrates? Oops, I don't even have my chat window open. Sorry. Yeah, sorry I missed that comment, Ashley. I'm not sure. What do you guys know about nitrates? Nitrates are good oxidizers, right? What do you know about hydrocarbons? Hydrocarbons are like gasoline. Gasoline is made up of a whole bunch of hydrocarbons. And hydrocarbons are good fuel, good reducers. And so take a look at nitroglycerin. Nitroglycerin has oxidizer. In fact, it has 3 nitrate groups on there. Now, normally I told you that nitrate likes to have acid, but it doesn't it doesn't absolutely have to have acid. In this case, it's got plenty. This is like if you let's say you're the nitrate, you're the predator, if you're the predator, you don't have to go seeking food. The food is right here for you, attached in the same. And so this is like a caged, what do they say? Lion? This is like a caged gazelle. The gazelle and the lion or the tiger, or whatever, are in the same cage. You got 3 of them with 1 gazelle. These nitrates are going to eat it. This just takes a little hair trigger, and that's it. And so this is the electron rich. This electron rich here. Hydrogen is +1. We got three of these kind of things on here, And so this is not an ionic compound, but we could do the oxidation states here. We'll do the oxidation states according to your book, or according to the rules that I had posted there. So out of all these elements, hydrogen goes first at +1, and then oxygen goes next. Oxygen's at -2. Nitrogen should be, -3, but it doesn't go that way. In this case, we treat this as like a nitrate type species, NO3-. This one's very complicated. This one we need more. The structural way of doing this would be a lot better. But it turns out this nitrogen here is going to be, well, there's something funny about this. NO3. Yeah. Oh, there's something funny. Well, anyway, this comes out to like +5. minus 6 plus 5, minus 1, so minus 3, should be plus 3, it's plus 5. And so 5 plus 3 plus 2. The oxidation states are going to come out funny, but anyway, this is electron rich. Actually, this I probably should do with structure. We'll do this once we get to Lewis. This one's too complicated to use our rules for. The rules for oxidation, remember, rules aren't always perfect, you know. And I especially like the quote from Dr. Shell, who, you know, is MedCram, you know. Said the good is not the enemy of the perfect, you know. And so the rules are good, they aren't perfect, but you know, they're not the enemy. Some people expect perfection. We don't always have perfection, obviously. Anyway, so this is the electron rich, this is electron poor, and what happens is this is a very violent reaction. The reason this is a very violent reaction is because there's lots of energy. This is highly exothermic. And the other reason this is very violent is there's lots of gases. When this goes off, it's high energy, so all these are gases. Normally water is a liquid, but you know, it'll be a gas until it cools down. Eventually it's going to cool down to a liquid. But initially it's going to be a gas. This is going to be a gas. This is going to be gas. And so what happens is we take a tiny bit, nitroglycerin is a liquid. We take a tiny bit of liquid and it makes, this tiny bit of liquid makes a huge volume of gas. I think I did a calculation once. It's like 1 milliliter of liquid makes like, I forgot how many liters of gas. It's some pretty big number of liters of gas, and if that gas is formed quickly, you get something called a detonation. You know, shock wave, basically. Well, anyway, this is not one of the blue numbered problems, so let's move on. This is Nobel stabilized this stuff. This stuff is like a caged gazelle with three lions, basically, you know. And how do you make this stuff stable? Because it's like on a hair trigger. It's on a hair trigger. And so what Nobel did was he stabilized this by adding an absorbent material, and sawdust. So this is liquid, so this liquid gets absorbed into sawdust and makes it more stable. Dynamite's more stable. You know, liquid nitroglycerin is very dangerous. Actually, this was a blue problem. What is it? Okay, so how many grams of carbon dioxide are produced in an explosion of 21 grams of nitroglycerin? Now, the density of nitroglycerin, we don't have. Okay, but it's easy to look up. 21 grams of nitroglycerin. So we did 21 grams to moles, moles of nitroglycerin to moles of CO2, moles of CO2 to grams of CO2. So it's just, you know, grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. We just need the molar masses, mole ratio from the equation, molar mass. Okay, skip that one. Soaps are produced by the reaction of sodium hydroxide and naturally occurring fats. So this would be a fat. When you look at fats are also fuels. They're electron-rich type species. When you look at this fat, it consists of carbon, hydrogen, and oxygen. Those are fats. So I forgot to add fats. You know, I had what did I have? I had alcohols, ethers, sugars, and fats are all made up of carbon, hydrogen, oxygen. All of them burn to CO2 and water. So when you eat fats, you know, eventually your body is going to metabolize this. You're going to exhale all that carbon as CO2. What we can do is we can take fats and hydrolyze them, or not hydrolyze them, but you know, break them apart with sodium hydroxide. Sodium hydroxide is good at dissolving fats. We got fat here. We'll break it apart. This is called a fatty. Well, this is called glycerin here. Glycerin is an alcohol. And so we make some glycerin, and we make the salt of the fat, basically. The lost compound is the soap. So this is the soap here. Soap is pretty interesting. Calculate the interesting properties it has, which we'll talk about later. Calculate the number of grams of sodium hydroxide required to produce 323 grams of soap. So this is the soap here. Oops. Here. And so we're just going to go from 323 grams of soap to moles of soap. Now we have different soaps, you know, depending on what fat you use. You know, like palm olive. Palm olive soap uses palm oil or palm fat and olive fat to make soaps. And the formula, of course, is going to be different. And so this is just for this particular soap here. And so we go from grams of soap to moles of soap, moles of soap to moles of fat here, or no, moles of sodium hydroxide. Moles of sodium hydroxide to grams of sodium hydroxide. So grams of fat to moles of fat, moles of fat to moles of sodium hydroxide, the gram conversion. One way to make sodium thiosulfate. Sodium thiosulfate is also a pretty good reducing agent compared to sulfate. You know, when we throw in that sulfur in there, sulfur is a lot more electron rich than oxygen, okay, which is used as an antidote to cyanide poisoning. So sodium thiosulfate, I wonder how that works, you know, what the mechanism for that is. That would be pretty interesting. Cyanide's like carbon monoxide. You know, cyanide attaches to iron and hemoglobin and prevents oxygenation of your blood. It's described by the equation. So we take some sodium carbonate and sodium sulfide and some sulfur dioxide. You know, what kind of reaction is this? Well, the reaction here is, is this a redox reaction? It's not a metathesis, because metathesis, we'd be switching around the ions. So here, carbonate doesn't exist over here. So it's definitely not metathesis. So we'd have the ions, where we should have some of them at least. And so this is either redox or acid base. One way to tell if it's redox or acid base. Now this doesn't look acid base, but we haven't talked about Lewis acid base yet. And so this could very well likely be a Lewis acid base reaction. But there's an easy way to tell by looking at oxidation states. And so sodium gets assigned first at +1 here, and oxygen at -2, and that leaves carbon at +4 here. And then sulfur, sodium gets assigned first, +1, sulfur is going to be -2 in that case. Oxygen gets assigned first, this is -2, and then that leaves sulfur at +4 here. And then sodium gets assigned first at +1, oxygen at -2, and then that's like +2 -6 is -4, and so each sulfur must be +2 to give us a total +4. And then over here, carbon is, well, oxygen gets assigned first at -2, carbon's +4 here. So let's see what happened here. Nothing happened to the sodium, that's fine. Carbon went from +4 to +4, nothing happened to carbon. Oxygen went from -2 to -2. Nothing happened with the oxygens. Sulfur. This sulfur went from -2 to +2. So it lost a total of 4 electrons. You know, -2 to +2 is 4 electrons. This sulfur went from +4 to +2. So this sulfur gained 2 electrons. So interesting thing happened here. The sulfur and sulfide lost, and the sulfur and sulfur dioxide gain. And so this is the oxidizing agent here. This is a redox reaction. This is a reducing agent. Sulfide is usually a good reducing agent. You know, in NaC, we have this kind of link here. You know, this is the cysteine part, N-acetylcysteine. And so this is a good reducing agent. The sulfur here is -2, you know. Sulfur is a good reducing agent because it's big, you know, it's a big atom compared to oxygen, you know. And so sulfur. So something like this, sodium sulfide, you can burn this stuff, you know. If you try to catch it on fire, eventually you can catch it on fire. Or sodium oxide, you really wouldn't be able to, it's like trying to burn rust, you know. Can you burn rust? Well, oxygen has, 2 electrons, so maybe you could lose those. No, if you try to burn rust, it would be hard, because the oxygen, and the iron's not going to lose any, it's already iron 3. But, if you look at the equivalent sulfur containing compound, Fe2S3, yeah, this is potential to lose those electrons there. How many grams of sodium carbonate are required to produce 681 grams of sodium thiosulfate? And so here, sodium carbonate, we want 681 grams of sodium thiosulfate. So grams of thiosulfate here to moles, moles of thiosulfate to moles of sodium carbonate, moles of sodium carbonate to moles, to grams. So this is standard. So we see the pattern. Grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. Let me just say that. So it's just getting the mole ratio, which is already given. We don't even have to figure it out. But we do have to figure out the molar masses. Molar masses, you could also, Wikipedia has molar masses there. If you're already good at doing molar masses, you could save time. Just get them off Wikipedia. Hard water scum that forms a ring around the bathtub is an insoluble soap. Some soaps, like sodium salts are soluble, but calcium salts aren't all soluble. It's because of the charge. Sodium's +1, calcium's +2. Electrically, a +2 is much more reactive than a +1. And so this is, this would be a good soap if it was sodium with this. Now it's going to be hard water scum because there's calcium. In fact, if you have hard water, you get these rings. Because you take this soap and it just precipitates. It makes this precipitate. And so you take this soap and it just precipitates. When you look at this reaction, this is called metathesis. I don't call it double replacement because double replacement is AB plus CD. But if we don't have the AB plus CD pattern, a lot of students are totally lost because all they know are simple patterns, But conceptually, of course, there's metathesis because all we're doing is we're switching the anion. We're switching the anion from sodium to calcium. And calcium loves this anion. It loves it so that it precipitates. Sodium, sodium doesn't love it that much. But calcium does. And this is the soap scum, so we get a precipitation. So this is metathesis. But it doesn't fit our pattern of AB plus CD. And so this is why I don't call them double replacements, because if I called everything double replacement, then everybody's looking for AB plus CD, but it doesn't always happen like that. Where does the calcium come from? Calcium comes from your water supply. Your water supply contains calcium ions, sodium ions, a whole bunch of other anions, cations, and it has to have anions because of electrical neutrality. It just can't contain calcium ions, but the anions are going to vary. Chloride's a common one, and then there are others. And so we could ignore the anions because there's strong electrolytes, otherwise it would have precipitated out. And so the calcium ions in your water supply, this is soap. And so if your soap hits hard water, then it forms soap scum. Soap scums that precipitate, and this is the driving force for this. Now, calcium salts, are going to be a lot less soluble than sodium salts because of the higher charge. Those are the types of things you notice, like even in the solubility rules, you have two types of people. You have two types of, one type of person says, oh, if it's not on the solubility chart, forget it, Then you have the other type of person who can look at for patterns, and say, okay, they can make a reasonable, maybe a reasonable guess as to what's going to happen. How many milligrams of scum can form from 616? So we'll take 616 milligrams of soap. So we go milligrams to grams, grams to moles, moles to moles, moles to grams, grams to milligrams. And so just do a little bit of extra work here. I don't like this here. I don't like too many variations. This is correct. This is correct. We can just do we can do the molar mass is a millimolar mass. If we do millimoles and milligrams, and the same thing, milli, 1,000. But I don't like this. The reason I don't like this is because if you see too many variations, then it's a lot harder to catch mistakes. And so I totally recommend to just go, even though it's more work, you're less likely to make mistakes if you use. This is why I say, you know, on the test, stick to the, you know, the basic conversion factors and then string them together rather than making fancy new ones. If you make fancy new ones, there's a one-time use, you know, how often do you use that? You stick to the basic ones that you use over and over again, then it's a lot easier to memorize. Why do you want to memorize things? You want to memorize things for speed. You know, this is like drills. You memorize how to shoot a basket or something like that, or you memorize how to hit a tennis ball, you know, or do whatever. I don't know. I'm not a big sports person, but you do these drills. But I remember, you know, playing sports, hitting the baseball, you know, this kind of stuff. You do that. This is the same thing, you know, you do this repetition to build up that thing. And so when you do too many variations, fancy variations like this, it doesn't help in memorization. This, you know, this is 1,000 milligrams per gram. And then do, you know, it's going to be 1 mole of soap. I'm just going to call it. This is a particular, so I don't want to write that whole formula, so I'm just going to call it 1 mole of soap is 306.45 grams of soap. And so we could use abbreviations here. Although lots of different kinds of soap, but this is for this specific soap only. You know, this doesn't work for all soaps, of course, because you got different formulas. And then the mole ratio, you know, I don't want to do the millimole. I'll just say 1 mole of calcium, the soap scum. In fact, I'm not going to call it, I'm just going to call it scum. 1 mole of scum for every 1 mole of soap. Or no, 2 moles of soap, sorry. 1 mole of scum for every 2 moles of soap. And the molar mass of the scum. There's lots of different scums depending on what soap you use, but this particular one weighs 607.00 grams of scum per mole of scum. And then what we'll do is we'll just convert it to milligrams, you know, 1,000 milligrams per gram. Okay, and so the advantage of this is it just builds repetition, you know, and it's easier to memorize certain things. And also it's the same pattern, you know, milligram, the same core pattern. The core pattern here is grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. And we just add 2 things. We add these 2 things at the end, you know, the milligram thing here. That's it. And so if you have the same basic core pattern, then what you're going to find out in hard problems, in harder problems, there's just, you're trying to reach the core here. You're trying to reach the core. And so what you do is you do additional steps like this. We had to do an additional step, but sometimes you have to do multiple steps to get to our core here. And once we get to the core, then we might have to do multiple steps to get what we want, you know, but we're shooting for this, you know, in advanced problems, where we have to do extra steps that we tack on either at the beginning or tack on at the end. And that's a hard problem in stoichiometry. Sometimes we do, there are other patterns though that we look at as well. Pig iron from a blast furnace contains several impurities. Okay, when we get to impurities and mixtures, that's a harder stoichiometry problem. That's where we do the extra steps, but we're shooting for the core, you know, of our stoichiometry map. One of which is phosphorus. Additional iron ore rust is included with pig iron in making steel. The oxygen in the ore oxidizes the phosphorus by reaction. Okay, so here's the iron ore, which is rust. So we take rust and we react it with phosphorus, then the oxygen and the phosphorus react. This is a redox reaction. And so what's happening here, Oh, this is kind of a weird redox reaction. Let's see. Because they're saying the oxygen in the ore oxidizes. That's wrong. This is wrong, unfortunately. The oxygen in the ore oxidizes. That's wrong. The oxygen in the ore doesn't oxidize anything. We have Fe2O3. Oxygen is already happy. Oxygen doesn't need to oxidize anything. Oxygen's happy because it's already -2. Wrong color. Different color. Oxygen's happy, it's -2. However, iron is +3. If you look at your redox chart, iron 3+ is a moderate oxidizer. And so iron 3+, if anything, why would oxygen take electrons? Oxygen doesn't want any more electrons. It's the iron who can take the electrons. And so this is unfortunate, but it happens. You know, there are always mistakes. You know, this is why there's called peer. This is why there's people called them referees. You know, for scientific journals, and this is why there's something called peer review. You know, where people look for mistakes. So we're going to just review this here. Well, this is a mistake. This +3. In fact, we saw, you know, thermite, you know, this is acting as an oxidizer. Yes, not because of the oxygen, because of the iron. And then phosphorus is 0 because it's an element. And then over here, oxygen is -2. So -2 times 10 is -20. -20 divided by 4 is +5. So each phosphorus is +5. And then iron is 0. So iron went from +3 to 0. So each iron gained 3 electrons. Oxygen went from -2 to -2. So nothing happened to oxygen. Phosphorus went from 0 to +5. So each phosphorus lost 5. And that's why we have these ratios here. You know, you got to make sure the electrons balance. Because if iron gains 3 and phosphorus loses 5, well, that doesn't quite work out. So we look at rearranging the numbers so it works out here. And so they should have said the iron in the ore oxidizes phosphorus, not the oxygen in the ore. If a sample of the remains from the surface contains 802 milligrams of tetraphosphorus dicoxide, what mass in grams of Fe2O3 was used in making it? And so we're just going to go 802 milligrams of P4O10 to grams, grams to moles, moles of P4O10 to moles of rust, Fe2O3, to grams of rust to milligrams. They're going to use this millimole stuff that I don't like. You know, I don't like this. But just because I don't like it doesn't mean I'm right. You know, you're welcome to write it like this. But when you're learning, you just want to, you know, keep things simple. When you're an expert, then go ahead and do all the fancy stuff, you know. But when you're learning, just do the basic drill. Okay. Let's see this. This is combustion of nitrogen to form NOx. This, you know, this is air. And so does air burn? Air burns only at very extreme conditions that you find in diesel engines and automobile engines. You can get the air to combust. And nitrogen is fuel, oxygen would be the oxidizer. Oxygen is closer to fluorine. You know, both of these want electrons, but you know, Oxygen wants it more. So anyway, what's this? Sodium carbonate. Sodium carbonate's used for lots of things. Let's see what they say. The solvay process is a multi-step industrial method for the manufacture of sodium carbonate, which is also known as washing soda. Although most of the industrialized world utilizes the solvay process for production of sodium carbonate, it is not manufactured in the United States because it can be found or it can be obtained at lower cost from a large natural deposit in Wyoming. Wow, I didn't know that. And so I guess they just mine this stuff out of the ground. All right. How much sodium chloride is needed to completely react with 83.0 grams of ammonium hydrogen carbonate? Hydrogen carbonate is also called bicarbonate. So more commonly, this is called ammonium bicarbonate. So sodium chloride and ammonium bicarbonate. What kind of reaction is this? This is a metathesis reaction here. I can see it because the ions are just swapped around. And so when we look at this particular reaction, battery issue. The battery's about to die. It just died. This I see as this is a metathesis because metathesis we're just looking for ions that like each other. So we have a sodium ion here, we have a chloride ion here, we have an ammonia ion here, and we have a bicarbonate ion here, or hydrogen carbonate, ion there. That's bicarbonate. And so what we do is we just see maybe sodium prefers bicarbonate, so we put sodium with bicarbonate. Maybe ammonium prefers chloride, so we put ammonium with chloride. Is there a driving force for this? And so let's look and see if I don't see any driving force for this. This sodium salts are soluble. This is aqueous. And ammonium bicarbonate doesn't decompose. Ammonium hydroxide, so what am I doing? I'm looking over here. Sodium bicarbonate doesn't decompose into gas unless it's very high temperature. Very high temperature, probably sodium carbonate will decompose. If I heat up sodium bicarbonate to very high temperatures, it probably will decompose into CO2 plus whatever, try to figure it out. Same thing with ammonium chloride. Ammonium chloride is not going to decompose. Ammonium salts are soluble. What else? We aren't going from stronger acid to weaker acid. No precipitate, no gas, no stronger acid to weaker acid. This is NR. There should be no reaction here. And so I disagree with this problem. This problem, there should be NR, no reaction. That's fine to disagree. I have my reasons for it, but, counter to that, somebody, the author could argue, well, you didn't see this, or why not that, Lately, a lot of stuff, because there's a lot of coronavirus stuff going on right now, but I don't really see good scientific arguments happening, Like, for example, some people might hypothesize that, masks might do masks might be effective at lowering the aerosolized droplets, or what else, And then there are people who are saying masks are totally ineffective. Well, I can see the arguments for saying masks are effective, but I want to see the arguments for masks are totally ineffective because I want to be convinced. I want somebody to convince me. But a lot of these arguments are just that. Why are masks totally ineffective? Because I say so. I say so. That's not an argument, a scientific argument. I need some kind of backing or some kind of thing like that. Recently I watched this thing about, is it possible, that the coronavirus could have originated from the Wuhan virus lab, And there are arguments for that because it just makes sense. You know, there's lab and there's lots of accidents. Accidents happen all the time. You know, the worst industrial accident in the US was in Texas City, you know, the Grand Camp explosion, those two French tankers carrying ammonium nitrate. That was the worst accident. I guess I was wrong. It killed like closer to 600 people. You know, can you imagine, and including a whole bunch of school children who went out to watch the beautiful orange smoke. You know, when you see orange smoke, stay away. You know, you see orange smoke, yeah, get away as fast as you can. Yeah. So anyway, accidents happen all the time. You know, Bhopal, India, thousands of people died from the chemical spill there, you know. And so it's not totally unreasonable to see maybe it was a lab accident. Maybe that's how the coronavirus got there. And then there's some other observations. Other observations were that there are a group of scientists, like in Australia and elsewhere, who have been trapping animals and then looking for the source, you know, of the coronavirus, vats and with other animals that were at the market. You know, they're testing these animals to see if they indeed do have SARS-CoV-2, but they haven't found it. And so there are some observations that lead one to suspect that it is a possibility. But then you hear these people arguing against it. No, that's not possible. It came from the food market. But you know, what are the arguments for that? And it's one of those things, like, because I say so. And so a lot of this stuff, you know, because I say so, or because listen to me, you know, or why? Because, you know, these aren't real arguments. So, you know, I want to be convinced. I want to be convinced that it did not come, you know, from a lab. I want to be convinced, you know, or likewise, somebody will say, okay, I want to be convinced that it did come from the lab. Convince me, you know, that kind of thing. What are your arguments for that? And so this is a normal part of scientific discourse. Normal part of scientific discourse is people can disagree, no problem. But the way people should argue their point of view is they should present some observations, you know. They should present some, you know, factual experimental observations, you know, this type of stuff. But, you know, then there are those, you know, there are those groups that want perfect, you know, they're looking for perfect sound. You know, sometimes you have to connect dots in certain ways in order to make progress. So here, I disagree with this. There should be no reaction occurring here. There's no driving force. No driving force, expect no reaction. So let's skip this one. It's not worth wasting time on that. If somebody sees an argument for reaction here, of course, let me know. You know, that's normally the way science works. But we welcome it. We welcome challenge. You know, scientists welcome criticism. And harsher the criticism, the better, because then, you know, if your ideas can survive harsh criticism, then they're good ideas. You know, you want the biggest critics. You want the most vocal critics to attack your work. And then then you know how strong it is. You know? And so I welcome criticism. I like it when there's discourse. I don't like it when things are shut down, like, you know, the idea somebody proposed, it might be an accident, and then it was shut down. So, you know, I don't like that. Well, anyway, going back to this, byproduct, actually, it's time for a break. So let's take a break for 15 minutes, and then we'll start up again after the break.